found is that even physics professors, like all of the physics professors, actually struggle to solve this problem because even though it's an introductory physics problem, this is not the kind of problem that they assign to their students. So they had to think on their feet, right? And there are two different things that they have to think about. One is how much is the kinetic friction, but the other thing is how long does it take for the wheel to start to roll without slipping. And notice that it turns out that these two things conspire in opposite direction. So if there is higher coefficient of friction, then it takes a short time for the wheel to lock in and start to roll. And if there is smaller coefficient of friction, it will take a long time. But the final energy that is dissipated in the form of heat and everything before the wheel locks in is the same regardless of the coefficient of friction. And so, the final speed actually is independent of the coefficient of friction. Now, notice that even faculty had very difficult time solving this problem. And oftentimes they started out only focusing on one variable or the other. By the way, you can solve this problem using either, conservation of angular momentum, which is conserved about the point where the wheel first touches the ground. And since the angular momentum is conserved, the coefficient of friction cannot actually determine the final speed at which it rolls without slipping. The other way to do it is to use equations of linear and angular kinematics, and then finally set v final to r times omega final, and you'll see that the coefficient of friction drops out. But the point is that angular momentum conservation is tricky because you have to think about the point about which angular momentum is conserved, right? The point where the wheel first touches the ground and the frictional force is passing through that point. Now, what I would say is that faculty, even though they struggled to solve this problem, they knew how to solve problems. In other words, the kinds of heuristics that they were using clearly told us that they knew, that there was something about thinking like a physicist. They started out with doing an initial qualitative analysis, thinking about what was given, where they were going. Some of them even went to the board and drew a diagram. They thought about limiting cases. What happens when there's no friction? Or what happens when there's infinite friction? And of course, those limiting cases may not help you in this particular problem, but that's a really good heuristic that we should be teaching our students. Also, we found that faculty were using analogies with familiar situation, like what should happen, what happens to the wheels of an airplane when it's landing on the ground? How will the kinetic coefficient of friction determine the speed at which it rolls, right, without slipping finally? And those are all really great heuristics, thinking about limiting cases, thinking about analogies, thinking about predicting what the solution would be initially before actually moving forward and planning the solution. What we found is that students, on the other hand, were all over the place. Like the students who were interviewed, they actually, didn't use any systematic approach, and they kept going in circles. So there is definitely something to be said about thinking like a physicist and using effective problem solving heuristics. Now, you have to actually say that students actually do not come equipped with being systematic in their approach to problem solving. And we have even found that if you're systematic in your approach, students are likely to solve much more complex problems than they otherwise would if they were actually not clear on what good problem solving heuristics are. Like trying to actually not think about which formula to use in the situation, but thinking about setting up the problem, thinking about what's given, what we are finding, drawing a diagram, thinking about predicting some features, thinking about analogies with familiar situation, thinking about limiting cases, thinking about which principles of physics would be useful, dividing the problem into sub-problem if needed. So these are things that we should really be teaching our students. That is one thing that we learned is what it means to think like a physicist, something that everyday life doesn't teach us, because everyday life doesn't make us very systematic in our approach to whatever problem we are solving, whether it's about finance or how to get from here to there. And so the point is, we need to actually teach it explicitly to our students, and it's important to reward students by giving them grade based upon showing your work and doing a an analysis that is actually systematic, that actually makes it clear what your thinking process is when you're solving the problem. And then we saw that students were solving problems much better. The other thing that we saw that was very interesting about this research is that this was not the only problem that was given to physics faculty and students. We gave them another physics problem, which is this problem, which is the ballistic pendulum problem. And all the people from physics will recognize this problem because this is a problem that you give to your students all the time, right? So basically, there are two putties that are actually hanging from the ceiling. One of them is raised to a certain height, and you let go, and it collides with the other one. The two things stick, go to a certain height, final height. And the question is, how would you find the final height in terms of the initial height? Now, notice that at one university, this problem was given as an open-ended problem, but it was also given as a multiple choice question to students from 2,000 students from maybe 14 different universities in the US. And what we found here, I'm showing you what happened in the multiple choice case after instruction. And you can see that what it shows is that, like you have to actually use both mechanical energy conservation and linear momentum conservation for this problem, because when the putty is going down, you have to figure out what would be the speed of the putty right before it collides with the putty B, and that will be mechanical energy conservation. When the collision is taking place completely inelastic, that is momentum conservation. And then when the two things go up again, that is mechanical energy conservation. Notice that only 27% of the students after instruction provided the correct response. Many thought either one of them is needed or the other one, but not both. And what I would say is that physics professors at these universities, who were asked to give this problem to their students, they were also given, by the way, that spinning wheel problem. And they were convinced that their students would ace this problem because some of them even said, oh, I have just done this problem in my class, so I know they'll do really well. But that spinning wheel problem would be really hard for my students. It turned out that student scores on the spinning wheel problem and this problem is identical. In fact, 20% would have been random guessing here, right? So students did not do very well on this problem. And if you really think about the complexity of this problem, it's quite difficult for beginning students because you really have three parts that are temporally separated. When this thing is going down, you're talking about mechanical energy conservation. When the two things are colliding, that's an inelastic collision. You have to use momentum conservation. And when the thing is going up, that is again mechanical energy conservation. So the point is, like, if faculty are thinking this is too easy for their students because they have thought about this problem a lot and this has become obvious to them, they are really not going to be able to do a good job of teaching their students, because the complexity of a problem not just depends on its inherent complexity, but also on how much familiarity and intuition you have built about it. So if you really want to help your students, you have to put yourself in student shoes and think about the difficulty from their perspective in order to scaffold or guide them in a way so that they learn better. Because if you think, oh, this is obvious, this is easy, just because it's obvious and easy for you, like that ballistic pendulum problem, you are going to underestimate the difficulty of problems, and you're not going to be able to guide and scaffold students learning in an appropriate way. Okay, so now I'm going to move on to my other study. And this one is focused on reflection on problem solving. By the way, all the studies that I'm talking about are all published studies, either in American Journal of Physics or Physical Review Physics Education Research. So if you are interested, you can send me an email later and I'll send you all the details. But this one is focusing on, do people actually use problem solving as a learning opportunity? Because we want students to use problem solving as an opportunity to learn. So if I did something wrong, I should actually reflect upon what I did wrong when I get my solutions, and so that next time I do not make that mistake, right? Unfortunately, what we have found in our research is problem solving is often a missed learning opportunity. In other words, unless you give students deliberate prompts to correct their mistakes, by giving them some reward, like grade rewards, you will see that oftentimes students will not learn from the mistakes that they will make. And later on, when you give similar kinds of problems, they will again make the same kind of mistake. So this is something that we have actually done both at the level of introductory physics and in advanced physics such as quantum mechanics. So these are the references for introductory physics. I'm going to actually talk to you today and show you data on what we found in advanced quantum mechanics, which is undergraduate upper level quantum mechanics for third year, fourth year students. And what we actually did was we had an intervention group and we had a control group. And the difference was that students in one group were asked to actually correct their mistakes on, say, for example, things like quizzes or exams, midterm exams, for a certain amount of points back. So for example, like when the students were given their midterm exams back, they knew that they had done some mistakes on, say, problem 2, and then they had only gotten 5 over 10. They were not told exactly what they needed to do, but they were told, okay, so this is Friday, here is your midterm back. Why don't you go home, look at your books and notes and correct your mistakes and bring it back on Monday for 50% of the points back. And what we've, and by the way, this is similar to the kinds of things that we have done in introductory physics. And then after students actually gave the corrected solutions, they were provided the correct answers to all of the problem. So they were given a solution similar to the students in the control group in which they were not asked to correct their mistakes. Now we were trying to actually see if you later in a final exam, for example, give similar problems, that use the same principles of physics, would student performance on those problems be the same or different in the case in which students were just provided the correct response and not asked to correct their mistakes for certain points back versus when they were asked to correct their points back, right? So let me actually just show you the data here. So this is the comparison group and this is the incentivized group. And by the way, we have since done it in many, many different courses, but this is basically for quantum mechanics course. And so what you see pre means like how did they do on those kinds of problems the first time they solved those problems. And we have divided students into 3 categories, 34%, 35%, or 65% and 96%, and this is the performance of all of the students. And this is like how did they do the second time on similar problems after they were actually not given incentives to correct the mistake, or they were given incentives to correct the mistake. And you can see that initially there was no difference between the two groups. But when they were asked to correct their mistake in this group, you can see that the students who had not done well initially actually ended up doing a lot better. And here again in the middle group, they were doing a lot better. Of course, people who have already done well, they are not really benefiting from this activity, right? So I really strongly recommend that you do this kind of activity because otherwise students will not necessarily benefit from the correct answers that you're actually providing to them. That means the solutions that you're providing. And this is something that will not take you very much time because it turns out that the second time when students struggle productively with their homework, with their notes and other resources at home with the same problems, they actually learn from those things. So it provides an opportunity for this productive struggle that helps them learn. And that is why you see that later on, students end up doing much better on those kinds of things. So we actually also interviewed 6 students who had not done well the second time and asked them, why didn't you learn from those solutions that were provided? And they said things like, oh, I don't really like to look at the solutions that my instructor provides because it really pains me to see, that I have done poorly. Or they said, oh, I don't think that I thought that those kinds of problems will show up, those similar kinds of problems will show up again on a later exam. So that's why I didn't study those things that the instructor is providing to me. But I think that this is not a really good thing. And we should really be actually helping our students develop a good knowledge structure. Even quantum mechanics, that may be, different paradigm from classical physics. We still have a very well-defined knowledge structure in it, and students should be given incentives and support to develop a good knowledge structure. And they will do this if you give them incentives, great incentives to correct their mistakes and productively struggle with the kinds of difficulties that they are having at their own pace at home by correcting their own mistakes. Okay, so I'm going to move on to talking about my third study now. And this one focuses on how to help students develop a good understanding of quantum mechanics concepts, right? So, I mean, of course, classical and quantum paradigms are different, and even if a student becomes expert in classical physics, when they actually go into learning quantum physics, they again start struggling because now, for example, concepts such as position and momentum, these things are no longer deterministic variables, like they were in classical physics. Now these things are operators that act on states in Hilbert space. And as they say, no one can hear you scream in Hilbert space, right? So I think that we really need to think very carefully about how to help students develop a solid grasp of this new paradigm, quantum mechanics. And it's particularly important now in this 21st century because we are going through the second quantum revolution. Quantum computing, quantum network and quantum internet and quantum sensing, these things are big things. And our ability to manipulate quantum systems and the way that we are able to actually control them is unprecedented. And so quantum industries are burgeoning. Whether you think about quantum computers made by IBM or Google, I mean, like, maybe right now we are still in the vacuum tube era of the classical computer, so we still have to get to the architecture, like to the transistor of quantum computing. But that's why there is so much interest in this area. There's so much going on here, but students are struggling to learn quantum physics, and that's foundational in order to actually do this. So we wrote an article in Physics Today with my collaborators on taxonomy of what are the kinds of difficulties that students are having in learning quantum physics. And let me just give you a few examples. So, like, for example, uh, one of the questions was, if your quantum state is and by the way, these studies were done with students at 9 different universities. These are upper level undergraduates and even graduate students. So more than 200 students participated in these studies. And they were given a quantum state, which was a linear superposition of the ground state and first excited state. Different faculty use different notation, slightly different notation, but it's the same thing depending upon what they had used in their classes. And one question was asking, what's the probability of measuring different values of energy, right? And what we saw is that across those different universities, 67% of the students provided the correct response. And the most common difficulty was between individual measurements versus expectation value. And again, as I said, today we are in this era of second quantum revolution when our ability to manipulate quantum systems is unprecedented. So we are not just going to talk about expectation value. These individual measurements are things that people can actually do in the lab, right? So it's really important for students to understand those things. But I would say 67% is not as bad. Now, the second part of the same question was asking about the expectation value of energy in the same state. And notice that this is part B of the same question. Now, it turns out that only 39% of the students provided the correct response for part B. Now, if you really think about it, the easier way to answer the second part, expectation value, would be to do it in a conceptual way and say, oh, expectation value of energy is the average value of a large number of measurements made on identically prepared systems, all of which are in this state. So if the probability of measuring energy E1 was 2/7 and the probability of measuring energy E2 was 5/7, then the expectation value should be 2/7 times E1 plus 5/7 times E2 plus nothing because all the other probabilities are zero. What we found is that a majority of students did not use the answer to the previous part to answer this. Even those who provided the correct response usually used an algorithmic approach. They used a memorized algorithm that expectation value means, you have to use integral psi star h. Psi h is the Hamiltonian operator that corresponds to energy. And so and some of them got lost in like the fact that there was an integral involved or what should be the limit for it, or like orthonormality, because this is a linear superposition of ground and first excited state. So notice, but actually if you really think about it, the way that we are teaching students quantum mechanics is all wrong. We are basically teaching them quantum mechanics as though it was some kind of boundary value problem, mathematics course, where all they keep doing is like, okay, one after the other, I'm going to solve H psi is equal to E psi, the time independent Schrodinger equation. And then, like plug in some value for expectation value using integral psi star H, whatever that operator is corresponding to that observable times psi. But this is wrong because students need to also be told what is the conceptual stuff behind all of this. If they really are not taught the conceptual aspect, the fact that expectation value is the average of a large number of measurements on identically prepared systems for each of those observables that you're talking about, then students will go through like some kind of algorithmic thing. And moreover, things will not stay in their brain. It'll get shampooed out after the final exam because we are not really helping them integrate the conceptual and quantitative aspects. Let me give you just one more example, of what kinds of difficulties we found across those 9 different universities. We asked students if the probability density of this linear superposition depends upon time or not. And the correct answer is yes, it depends upon time. Because, the time dependence of ground state is going to be e to the power minus I even t over h bar. And here for the first excited state will be e to the power minus I e to t over h bar. And so if you really look at the probability density, which is the absolute square of this, it will actually have those cross terms. So probability density should depend upon time. Another way to think about it is that this is not a stationary state. This is a linear superposition. But again, you can see only 43% of the students across different universities provided the correct response. And the most common incorrect response was, no, probability density doesn't depend on time because the time dependence is just an overall phase factor that cancels out. And that is, again, not true. And you can see that students are confusing stationary state with non-stationary state. But it is, again, not surprising because the point is that the most fundamental equation of quantum physics is time-dependent Schrodinger equation. IH bar del psi is equal to del psi over del t is equal to H psi and not H psi is equal to E psi, which is what the instructors are emphasizing. So they are emphasizing time independent Schrodinger equation where there is, the time dependence has already been factored out and not the fact that everything is a linear superposition. And again, I must emphasize that in this 21st century, when we are really doing quantum information science, quantum computing, quantum networks, and internet and quantum sensing, next generation of quantum sensors, it's really important for students to understand linear superposition, and this is noticed, just about one, particle. But you have to also talk about then what happens. You have many particles and you start thinking about entanglement and things like that. But the point is that what we found is that regardless of the university, independent of the teaching style textbook, we found common difficulties. And these were often due to difficulty in discriminating between related concepts. And these difficulties were universal, similar to the kinds of difficulties that have been found in introductory physics. So the question is, what can we do? So we are developing these research validated learning tools, which is an iterative process in which you think very carefully about what should be the learning objectives when you're trying to teach students about quantum measurement, or when you're trying to teach them about quantum key distribution, or you're trying to teach them about quantum teleportation, or you're trying to teach them about quantum time development. And then you have to think about what is the initial knowledge, what kinds of common difficulties students will have, and how will you take them as resources to help students develop a good grasp of these concepts. And then you can use a guided inquiry based approach. And by guided, I mean students and are the ones who are answering the questions, but you have to actually order them in a way where students are going through these worksheets and thinking through all of these things, because you cannot do the thinking for the students. They have to do the thinking for themselves, but you can actually design these things by doing a lot of interviews with students, by iterating it with faculty to make sure that they actually are commensurate with what the students' initial knowledge is, and they build on them in a way that after this, they are able to do well on the kinds of things that you really want them to do well on, which should be consistent with what your learning objectives want. What do you want students to be able to do? That's what the learning objective should tell you. So one thing that we are developing is quantum interactive learning tutorials. And as I said, They provide hint and feedback. They use this, guided inquiry-based approach, and they focus on bridging the gap between the conceptual and quantitative aspects of teaching quantum physics. And they incorporate computer-based visualization tools, and they keep students actively engaged. And notice that, the way that instructors use them is that they actually, for example, would do traditional lecture-based instruction. Then they would actually give some pretest that to see what students have learned after traditional instruction, like the kinds of things that I talked about, like a few examples I gave. And then they would actually have students work on the tutorial, these quilts, in small groups. Or you can even give them as homework, and then you can give a post test after this to see whether this has helped students or not, right? So let me just give you an example of a quilt on time evolution of quantum state. And again, let's say that your quantum state, you ask them some pretest question that was actually, one of them was about stationary state, say, for example, first excited state. And will the probability density depend upon time? And then one of them was linear superposition like this, and will the probability density depend upon time? And you can see that for this linear superposition, the probability density will depend upon time, unlike the stationary states, because there the time evolution is trivial, but here it's not, right? And so in this particular case, if the students actually, like I showed you that only 43% of the students provided the correct response after traditional instruction. So at that point, if you actually ask in the quilt, tell the students, okay, why don't you actually check with the computer simulation whether your pretest scores, responses are correct or not? Here I'm drawing for you psi star psi as a function of position for this particular state as a function of time. So these are like time lapse picture, like as time is increasing. And what you see is that actually the probability density does depend upon time. It's not the same. So then at this point, you have caused a cognitive conflict. Students are in a state of disequilibrium in the sense that they thought that the probability density shouldn't depend upon time because the time dependence should only be an overall factor, time dependent phase factor, and that's not the case. So this is a good time to provide them with this scaffolding support and guidance by asking them questions about why is it that the Hamiltonian of the system plays a key role. So the eigenstates of the Hamiltonian are special when it comes to time dependence of quantum state. And in those states, the probability density will not depend upon time. Whereas if it's a linear superposition like this, then it will. And then they are given opportunities to practice this thing across different kinds of problems. Like you don't want them to just like do it in one problem, like infinite square well on something, because then next day you give them simple harmonic motion oscillator, and they will not know that the probability density shouldn't depend upon time for a linear superposition of two states, to ground state and first excited state, for example, even for that problem. So you want to give students opportunity to decontextualize these things and see that they have broader applicability across different kinds of Hamiltonian, so long as it's a time independent Hamiltonian. So here I'm showing you just some examples of the kind of quilts that we have developed. These are the kinds of scores that students have gotten in percentage after traditional instruction, and how they have done after they have engaged with the quilt. And you can see that these are obviously a lot better. All the quilts are available on Fizzport, but if you want to actually email me to get quick access to it, I'm happy to send it to you. Some of these examples are really simple, but yet very beautiful, like Stern-Gerlach experiment. It's a two-state system, but it can teach students so much about quantum information science. Just two-state system that is relevant for quantum information science. Similarly, Mach-Zehnder interferometer, quantum eraser and things like that. Students get really excited about those. Quantum key distribution, again, very beautiful example that is very relevant for quantum information science. In fact, one of these we have already published in terms of its effectiveness in PhysRev PER. That is using non-orthogonal polarization states of light to actually, generate a common shared key between two people who will never meet with each other so that they can encode and decode information. So this is basically quantum cryptography. And the other protocol that we also have a quilt on is the one that uses entanglement. So actually like BB84, B92, and other protocols we have used for these kinds of things. We also have, developed a lot of like these things that we call uh, peer instruction tools. So these are things that you can actually use because they are basically think, pair, share multiple choice questions. Notice multiple choice questions can be very useful for classroom purposes. We can actually, an instructor can actually show that and then have the students discuss with each other the answers to those and then see whether the students actually provide the correct response or not after discussing it with each other. That's why it's called peer instruction. And then have an overall class discussion, because you may think that students get those ideas, but they are not so easy. Even if you say, oh, a huge trailer truck hits a small car, will the force exerted by like the big trailer truck on the small car be larger, smaller, or equal to that exerted by the small car on the other thing? You may have just discussed Newton's third law, but students may not see the applicability of Newton's third law in this context. Or you might say, a car actually goes and bangs into a wall. What is the force exerted by the wall on the car and the other way around? Again, people don't necessarily see the applicability of Newton's third law in those contexts. And so if you get students to think about those in a multiple choice way, and think, share, pair means whoever they are actually sitting next to, they discuss it with them. Notice that talking to other people really is a very effective thing. And here I don't have time to discuss this, but my own research also shows that you can co-construct knowledge. By that I mean, if I alone couldn't answer something and somebody else alone couldn't answer something, together we can figure this out by talking to each other. Because students actually, and in fact we find that almost in 30% of the cases, co-construction happens when neither student alone was able to solve a problem correctly. And we have found this in introductory physics courses. We have found this even at the graduate level, not just introductory physics, but also at the graduate level. So, and here I'm just showing you some results that if you use, say, for example, in quantum mechanics course, clicker questions, like for example, these think, pair, share exercises, which are multiple choice questions. This one, the purple one, the red one shows the students who didn't use it. They just had traditional instruction. And you can see that the percentage of students who are getting high scores is very low. On the other hand, the purple one and the yellow one are showing students who use these think, pair, share exercises for this particular topic in quantum, and their performances are much better. These are two different instructors. And we have seen the same kind of benefit in other cases. And notice that incorporating these kinds of things is a really good thing, because the other thing that research shows is that teaching by telling does not work. And you have to give students an opportunity to actually think about it themselves, organize their own knowledge structure, repair their own knowledge structure, and extend their own knowledge structure. And giving these kinds of multiple choice questions, in which they have to think about the answer, talk to their peers next to them, and then there is an overall class discussion about the correct answer, is very effective after doing traditional instruction. Because again, it provides that opportunity for productive struggle before students actually know how to think through these things and assimilate and accommodate these new ideas into their knowledge structure. So let me now move on to my last topic here. And this is going to be focusing on um, affective issues, improving students' self-efficacy, sense of belonging, and intelligence mindset in physics courses. So what is the meaning of the word self-efficacy? Self-efficacy is students' belief in their capability to succeed in a particular task, course, or subject area, and it can impact students' persistence and engagement. And it can also affect students' performance in science courses and engineering courses, even after controlling for their prior knowledge and skill. It can also impact their time on task. If I don't think that I'm good at something, I'm going to procrastinate. I'm not going to want to spend time on those things. So that way, like it's hurting me twice. It's hurting me when I'm actually in like, me wanting to procrastinate on something that I don't think I'm good at. And also when I engage with it, I'm anxious, and that anxiety is taking up some of my cognitive resources. Now, cognitive science says that whenever a person is actually solving problems, they have only limited resources in their working memory. In fact, they only have 5 to 9 chunks, regardless of who they are, when they're trying to solve a problem. And if some of those chunks are being taken up by the anxiety, then I have been robbed of some of those cognitive resources, and I'm not going to be able to do problem solving using all of my cognitive resources. So thinking about issues of self-efficacy and making sure that students actually don't have anxiety is really, really important. And students feel like they can do these things and they have a high sense of belonging is really important in making sure that students do well. Otherwise, they can go in a negative feedback loop, and anxiety can, make them do worse and worse in a course. I'm going to show you an example from physics. This is the famous sixth Solvay conference in 1927. One of the things you see here is that everybody is like, a male person. There's only one woman, Mary Curie, who's a woman. So again, if you look at, what is happening in physics conferences, in more recent times, okay, the situation only looks slightly different. If this is the situation, what do you think, like, people who are underrepresented in these disciplines are going to think about? So let me show you some data from my own research. And so here I'm showing you data from, those first year engineering courses that we ourselves took, in IIT, sorry, physics courses that all of us were required to take in our first year. Even in the US, it's the same way. So this is, in the US universities, what you see in physics one, which is for engineering and science majors, physics, chemistry, and math majors, I'm plotting on the horizontal axis their grades, and in the vertical axis is students' self-efficacy at the end of the course, given on a Likert scale. You know, I think I'm really good at solving physics problem. Do you strongly disagree, agree, those kinds of things, right? What you see is that if you look at people who are getting A grade at the end of physics one, this is Halliday-Resnick physics one, women who get A grade have the same self-efficacy as men who have B grade. And by the end of physics 2, this is the E&M course, electricity and magnetism. This is mainly mechanics. What you see, actually, there is no statistically significant difference between women who have A grade, their self-efficacy, and men who have C grade, their self-efficacy. Now, I must say, notice that it's not just your grades that matter. What also matters is how good you think you are. Like, so self-efficacy by itself is a really important thing, because you're not going to stay in a discipline if you really don't think you're that good at it, or if and you might actually drop out of that discipline, despite actually doing really well. So we could be really compromising on quality if we don't address these issues of low self-efficacy. In fact, I'm going to show you data from the same university, you know, of students, and showing that women are dropping out of science and engineering courses at with significantly higher grades than men are. So this is from computer science and engineering. This is not physics data, computer science and engineering. The top graph here shows, like, the vertical axis here is the mean grade point average, and this is the mean grade point average only in science and engineering. This is the which year the student is in, right? The top curve here is women who actually completed their their computer science and engineering major. This is also women who completed, right? The green one is men who completed. You can see women are clearly doing much better. They have much better GPA if they are completing computer science and engineering. What is shocking is that this blue curve here is for women who dropped out of computer science and engineering and went into some other discipline. And this is, men who are dropping out. You can clearly see that there's a huge difference in the GPA of men and women. And in fact, if you look here, in the fourth year, women who are dropping out have the same GPA as men who stayed. How is that possible? Like, we let these women actually drop out of computer science and engineering. Maybe they had lower self-efficacy. We didn't do anything about it. We just let them. We are compromising quality, as you can see, by letting those people who are, actually doing well, not giving them good support, not increasing their self-efficacy because they are dropping out. And here I'm showing you for physics, math, and physical science, physics, chemistry, and math, and the curves are very similar even here. Here I'm showing you students who actually drop out of different majors. And again, if you look at this, what you can see in engineering, 23% of the students who initially declare major drop out. In physics, it's the absolute worst. 38% are dropping out. Like, they initially say, I want to be a physics major. Then they're like, I'm out of here. here, like you can see, 65% of the underrepresented minority students who are physics majors are dropping out. So obviously here in engineering, it's like 28%. So obviously, like these people said, oh, I really want to major in this discipline, and then we are actually letting them drop out. So again, we are not really providing support, and obviously it's much worse for underrepresented minority students than if we include all students. And by the way, if you look at the GPAs, students' grade point average, based upon how many disadvantages they have, like for example, are they first generation student, low income students, underrepresented minority students, the more disadvantages they have, their GPA keeps going down. So again, it looks like the university is not even providing the right kind of support to increase students self-efficacy or whatever else they support they need to make sure that they actually feel valued and given and are given the right kind of scaffolding and guidance to actually excel in these disciplines. So one of the things that we have done here is we have intervened in our first year introductory physics courses, and initially we ran it as a study and we found huge benefits. So let me tell you what the study was. So basically in this study, which actually only takes 25 to 30 minutes at the beginning of the first physics course, like it's like first semester, first year, you've just arrived at IIT. Like in this case, it'll be you first arrive at University of Pittsburgh. And so these are huge classes. Like we are talking like several, seven and 900 students roughly, or more actually. So basically three instructors. So each of these classes is like more than 200 students, and three instructors participated. So, basically by recitation, I mean those are the problem solving classes in which not more than 40 students are there, even if in the lecture classes there are more than 200 students. And so what we do is at the beginning of this course, basically we do this short intervention that actually comes from people at Stanford University, where they found huge benefits of this in math courses in high school. So in the college level, what we do in these physics courses is that the instructor says to students, struggling is the only way to learn something new. And struggling is actually a very normal thing. Most people struggle to learn physics. So, and why are you in college? You're here to learn it. So be proud of it and pat yourself on the back, because when you're struggling, that means you're on your way to learning new things. And also failure and not being able to do something, when you're trying to solve a problem, is not really a failure. Brush your knees and get up and run again. Embrace your failure, because those are actually stepping stone to learning new things. And even Einstein said, if you haven't struggled, you haven't tried to learn anything new. And then generally the instructor says, I remember when I was in college, like we were struggling with different courses also. And actually, I've talked to my colleagues and they also say the same thing. And so I think that this is basically trying to normalize adversity and normalize struggle so that people actually embrace their struggle and be proud of it. And you view them as a stepping stone to learning new things, as opposed to as a threat to avoid. Oh my gosh, I'm struggling because I'm a woman. Oh, I'm struggling because I'm a minority person, and people like me are not supposed to be doing physics. Because when you actually don't have role models and when you have all the stereotypes around you, those are the kinds of things that make you anxious. So the goal here is to reduce anxiety, reduce procrastination, and increase enthusiasm for solving challenging problems, and ensure that students' limited cognitive resources are used for problem solving. I see that I'm running out of time, so I'm just going to quickly tell you what happened. What was the only difference in these two? Like some of the recitations and the recitations that were in the control that were the control group recitation, in which this intervention didn't happen. This was a 25-minute activity in which, initially students were given a sheet of paper on the first day, right? This is also like we are just arriving on campus. I still remember like arriving on IIT Kharagpur campus. So if the instructor in physics class gives us a like sheet of paper and says, write your concerns about being in this physics class. And students actually write a lot. And then you say, okay, stop. Within 10 minutes, everybody stops. Then they are actually given, on the screen, testimonials from students in previous years, which are actually real testimonials, which actually, these are students who have actually really done well in those courses. And some of those names are like, female names, some of them are male names, some of them are underrepresented minority name, some of them are white name, and everybody in their own way is saying the same thing. Hey, I was really concerned about being in this course, and then I realized that it was really about working hard, working smart, taking advantage of all the resources, and lo and behold, I ended up doing really well in the end. I actually started taking advantage of my instructor's office hours, my TA's, teaching assistant's office hours. I started working with other people. I started realizing that struggling is normal, and I started patting myself on the back and said, yes, these are challenging problems. I'll get through it, and be on the next step and on the next step. And lo and behold, that's the way it worked. And really, I ended up doing so well in physics, right? So everybody in their own way is saying the same thing. And then after they see these testimonials from students, they're asked to get together in groups of 4 or 5 and discuss with each other what they wrote on those sheets of paper. And also, why don't students realize that struggling is normal? And why don't students realize that struggling is actually a good thing? Because that is why you are in college. You are here to learn new things. So you should really be proud of struggling and use this as a stepping stone to learning new things. Now, notice when you frame it as why don't students realize, you want students to believe it. And so what I'm going to show you here, and I can send you the script for this, anybody who wants, I can send you all the script, because now we are doing it in all of our classes, right? And what I'm going to show you is that what we saw was, first of all, after this short activity, we saw that women were more likely to go and say, I'm so glad that you actually used half of the recitation class to do this. My anxiety is down. I'm feeling so much better. Some students are like, hey, who's in tower 2? Can we do our physics homework together? That sort of a thing. But what we also found is that, like in the control group in which this short activity didn't happen, there is a difference, overall difference in the performance of men and women here. On the other hand, in the social belonging group, there isn't. By the way, there was here I'm showing you the same data for men and women, and also for like white and non-white students, and we see similar trends even for those students. By the way, there was a colleague who was actually from Stanford who helped us, who was in cognitive psychology, who helped us actually implement this thing, and he did similar thing in biology, and they found similar benefits even in biology. So notice that these kinds of things are particularly helpful for people who actually need them, who are anxious about being there. Oftentimes, it's due to the fact that these people belong to groups that have traditionally been marginalized in these communities, like women in physics, or underrepresented minorities of all kinds, like first generation students, or students who didn't have, by first generation I mean whose parents didn't go to college and things like that. So what I would say is that we as science and engineering faculty need to realize that we are coaches for our students in our classes. And not only should we worry about the kinds of things we have traditionally worried about, which I would call offense, which is helping students develop effective problem solving strategies or helping them develop a robust knowledge structure. Yes, those things are important. But just like a tennis coach or just like a chess coach, you would also make sure that you actually strengthen students' defenses. It's really important to make sure that we create a classroom environment where all students, not just those who are from majority group, feel like they belong. They have an identity as people who can excel in physics and engineering. They have growth mindset. That means intelligence is something that can grow by working hard, working smart, taking advantage of all the opportunities. And failure is not really failure, but it's a stepping stone to learning. That's called, growth mindset, as opposed to fixed mindset. Oh no, intelligence is something that is immutable. And some those people are smart and I'm not. That is the wrong way of thinking about it. And you can do a lot in inculcating the right kind of mindset amongst your students. And even a short activity like that at the beginning can go a long way in increasing students' self-efficacy about how good they are at how good they are and how good they could be at solving physics problems. And these things can also increase their interest. When you are working in a low anxiety environment, it can increase your interest, it can increase your achievement goal. So these things are extremely important. And by the way, my own research also shows that if you do active learning where students are working with each other, but the learning environment is not equitable, and students like who are from marginalized group like women and other underrepresented minorities are not feeling like they can open their mouth because they're not feeling safe and supported, and they're worried about, oh, if I say something wrong, will these people say, oh, women can't do physics or something like this, then they will be really stressed and they won't really participate fully in that discussion, and they will not benefit fully from these participation. So it's really important that we actually make sure that all students feel supported, and we actually create this safe environment where students are proud of struggling and they use it as a stepping stone to learning. Now, we are doing this intervention in all of our introductory physics courses. If anybody is interested, I can show you, send you a video of our Ohio State condensed matter faculty, Roland Kawakami, who actually says that doing this intervention changed his own whole outlook to life, because his whole relationship to his students is totally different. And notice that this kind of thing also has implications for your research mentorship with your students when you're mentoring undergraduate or PhD students, and think about how to actually normalize adversity and make sure that you actually recognize students for making progress. I don't have that much time. I already have run out of time, but I would just say that we have also learned a lot of lessons from pandemic, and I can send somebody paper who's interested in these kinds of things, because we wrote these things in American Journal of Physics. So we gave written surveys and also interviewed 37 students. And what we learned from pandemic again is that students like synchronous classes if out of class and in class components are both incentivized by grade incentive. I can talk more about it if anybody wants, but also the human aspect of learning was greatly valued. So again, what I mean by human aspect is that during the pandemic, physics instructors were often asking, hey, how's everybody doing? Can I mean, I'm also having this issue in my home too. And students felt this personal connection with the faculty, and this human aspect, this really came out. Some people were showing their pets on the video, or like something, and even though it was 1 or 2 minutes, students didn't really want to miss those classes. And so humanizing learning, and many students said in these interviews that we wish that physics instructors would actually do these kinds of things even in normal class, because the distance between the professor and students is so large that we don't see them as a human being. And so if you actually went to your class a few minutes early and kind of bonded with the students and talked to them about how things are going and just connected with them, that would go a very long way in students feeling like you are human, and they would actually work harder in your courses, and they will never miss your class. So I think that just like humanizing learning is such an important part of actually being part of a teaching and learning enterprise, and being part of a university as a faculty. So I think that you should really think about coming across as students to human, because that, I think, was the biggest lesson we learned in the pandemic, in addition to all of the other ones. So I think at this point, I would like to take any questions. Thank you so much.
Yeah. Thank you so much, Professor Chandralekha, for sharing thought-provoking ideas and research results on non-traditional ways of thinking about learning in the class and beyond. Thank you, Professor Chandralekha.
Thank you. Does anybody have a question? Like, if you are on Zoom, you can just unmute yourself and ask.
I see that I noticed that there are a lot of participants also online. Now let us start the discussion. Questions? Let's invite from online participants first. You can unmute and speak if you have a question.
Just unmute yourself.
Good evening, ma'am.
Please.
Ma'am, when we are talking, I was listening to your talk. Ma'am, since in India, ma'am, we have a very diverse kind of candidates. How to take account the context, ma'am? Ma'am, different learners have different context. And within the classroom, like suppose we are teaching physics, ma'am. Then how to take account of their context, ma'am? This is the main question.
So when you say context, thank you. That is a great question. And when you say context, are you talking about like the prior preparation of students could be very different? So if the prior preparation of the students is very different, one of the things that, again, that really helps a lot is making sure that, you don't actually focus on the students who are in the top 25%. You actually focus on all of the students. And also, again, if you do active learning, remember I was talking about think, pair, share activities. Those are great activities to do in class because, like you can, students can learn a lot from each other, like when they are working with each other. And in your office hours, like if you actually have office hours, which is outside of class, it is really important that in those office hours, you prioritize the kinds of questions, whether it's your office hour or whether it's your teaching assistant's office hour, you prioritize the kinds of questions that is asked by students who are actually struggling, as opposed to somebody, who comes to your office hours just to show off. And it's like, oh, Dr. Singh, can you tell me more about your research on like black hole or dark energy or dark matter or whatever else it is? Because like I mean, that's not the time that the office hours should be spent on. Those people are just trying to actually impress the professor. So it's important to actually center the experiences of students who are struggling. Also, like there needs to be like outside of class support like that. Now, I would say that some students, some universities in the US have also started like different kinds of courses. Like my university actually does an honors version of the course and a non-honors version of the course. But the total amount of time on introductory physics is the same, right? But Rutgers University, for example, has something called extended physics. What they do is that, and same for extended calculus too. So extended physics 1 and 2, extended calculus 1 and 2. And what that means is that based upon a pre-test that you would give to students at the beginning of, like when the students arrive at IIT and you're actually just like give them a physics and math test at the beginning, just that, to see, who seems like, they already are on top of everything. And based upon that, you can actually recommend to students that either they go to the regular physics course or they go to the extended physics course. Now, the way Rutgers does it, like the extended physics course has twice as much contact hours. So if regular physics course, for example, has 4 contact hours, that one will have 8. But students will get the same course credit for both of those courses. And those 8 contact hours would mean that most of those extra contact hours are actually for recitations. So there will be more collaborative group problem solving for those students who are actually coming with lower prior preparation, because it's your job to actually think about ways to support those students and not just focus on the top 25%, because those students will do well regardless, right? So, and also in Rutgers, like those extended physics classes are half the size. So they are never like, if suppose the regular physics course is 200 students, this will be 100. If the regular physics course has like recitations, which are 40 students, this will be 20. That way you can actually give more individualized attention to students. But how you actually do your office hours and how you do out of class support to these students. And also, I must say, I cannot emphasize the importance, and I have done a lot of research, and if you're interested, like please email me on how much students can learn from each other, even without the support of a faculty. Because so what I'm saying is that, encourage students to work with each other. And again, if you create a low anxiety environment where students feel like, yes, they can work at their own time, on things together, that would be a really good thing too. Because the thing is, like all the time, there cannot be a faculty or a teaching assistant present, but students working with each other can actually do, help a lot. And we have seen that it doesn't even matter if initially like 2 students who had done C-level work, if they work together, what we see is that their performance improves significantly compared to students who didn't work in groups and work just individually. So again, if you're interested in that paper, I'm willing to send you that as well. I hope that answers some of your questions.
Yes, ma'am. Thank you, ma'am.
Thank you. Other questions, please?
Okay, there are a couple of questions from the audience who are present in physical mode.
Yeah, can you please actually, make sure that
So
I can hear those, because I'm not sure. Yeah,
just a second.
I was curious behind what was the motivation for this topic, or how did you start this research in this topic?
Thank you. So, it turns out that doing research in physics education is not a new topic in America. Okay. So, I mean, in America, actually, people like Fred Rife, people like Lillian McDermott, these people have doing this kind of research since the 70s. Okay. Early 70s. I'm talking about like literally like 1970, 71, those guys. So really, what had not been done before was like in advanced courses. So I am passionate about improving student learning of quantum physics. So that was something that I did for I was the pioneer in that field, because the point is nobody had ever done anything beyond introductory physics. Most people had only focused on introductory physics. I'm also very interested in problem solving, improving students' learning of problem solving. So that is an area that I work in. So, but the way that I really got into this thing is when I came to University of Pittsburgh as a faculty. That was a long time ago. I actually started teaching, and then I saw that students were not learning as much. And then, next to my building was Learning Research and Development Center, and there was this person, Bob Glazer, who's a cognitive scientist who has done a lot of research actually with physics as the context. Because one of the great things about physics and math in cognitive science is that they have a very well-defined context in terms of what is wrong and what is right. Just like chess, you can easily tell who's an expert in chess and who's not. In physics also, you can easily tell who's solving problem in an expert-like manner and who's not. And similarly in math, right? So these are such well-defined domains in terms of like studying these kinds of things that people like Bob Glazer, and then I met this guy who has Nobel Prize in economics at Carnegie Mellon University. His name, he passed away, Herb Simon. They now have a center after him, Simon Center. But the point is like, it's called Simon Initiative. But the thing is, those people became like, my mentors. And then there was another person at Carnegie Mellon University. His name was Fred Rife. Fred Rife is, again, as I told you, he was a pioneer in physics education research who's been doing it since the 70s. So he actually was a physicist who was a condensed matter experimentalist who has done work in low temperature physics. And then he had switched to physics education research. So I actually started working with these, talking to these people, and slowly, so I made a transition from a condensed matter physicist to this one also. So I mean, like, what I'm saying is for a long time, like I was actually doing both things. I hope that makes sense, like, so it was like a gradual transition. So it's not like overnight I learned about this field. But then when I started working in my own classes and my colleagues' classes, then I saw that yes, using these evidence-based approaches to teaching and learning really helps students. And so that's how, I did it. But now in the United States, there are at least out of, say, 200 physics departments that have a PhD program. There are 20 physics departments that actually have a PhD program in which PhD students in physics actually do physics education research. And so I have had like 19 students who have already gotten their PhDs with me doing physics education research, and they are mostly faculty members in other physics departments. And I have like 5 more currently who are working with me on PhD. So this is like a field that is very common in the United States. Other questions, comments?
Hello, ma'am. I just wanted to know, like, the data or the survey which you took for the research, was that limited to some particular universities, or it was over different types of universities? Like the quality of the students also depends on the university in which they study. So, what was the kind of data?
So when I was showing you all the data for quantum physics, all those quantum physics data, those were from 9 different research universities in the United States. So, for example, like University of Pittsburgh, Carnegie Mellon University, University of Colorado Boulder, University of California, Santa Barbara, UC Davis, those kinds of places. So all of them were large research universities. So all of, and similarly with that when I said that ballistic pendulum thing that was given to 14 different universities, they were also large research universities. So it's easier for me to actually collect data at large research university because there are other physics other people that I know at those universities, and it's easier to do it there. But you're right that like smaller colleges or minority serving institutions might have a very different type of like students. But I would say that maybe one of the things that we found very interesting was that even though these universities are different, and maybe instructor might make a difference in terms of like, oh, did 30% of the students get this wrong, or 45%, that kind of difference might be there, but the kinds of difficulties that students were having was very similar. So if students were confusing stationary state wave function with non-stationary state wave function, that was the same difficulty across the different institution, right? If they were not really knowing that expectation value is the average of a large number of measurements on identically prepared systems, and they were using some algorithmic approach, again, very similar difficulty. So what I'm saying is that you can classify student difficulties in only a few category, which is a really good thing, because you need to then incorporate those things in teaching and learning. You can't just say, oh, I'm not going to mention that students might think that huge trailer truck exerts a larger force on small car, and then students won't think about it. No, they will think about it even if you don't discuss it. So you might as well bring it up in your class, have the students discuss it with each other, and then have a general class discussion, so that students actually repair their knowledge structure and realize that no, Newton's third law says that forces should be equal and opposite. Accelerations of these things will be very different because the masses are different, and so huge trailer truck might not actually be impacted very much, but the small car might get thrown off. So I think that these were from similar kinds of institutions, which were all large research universities. So yes, smaller institutions might show different percentages and some different trends, and maybe they'll feel more supported. But I feel like these are research findings that, at least in terms of percentages, may vary, but the findings you'll see in other universities for some students would be similar. Thank you. Other questions, please?
Professor Chandralekha,
Please.
our director, actually, Professor Shantanu Chaudhary, is also online. I would like to now request Professor Chaudhary to share some insights and perspectives on the subject. Professor Chaudhary?
Thank you. But nothing much to share in terms of insight. But I would just like to thank Chandralekha for the nice talk.
Oh, thank you so much for having me.
Yeah, and I think you brought many of the issues to the focus. That is collaborative learning, in terms of actually doing the work and taking it back and trying to rectify the problem on their own by knowing these are correct result and coming back next time, which actually reinforces their problem solving skill and motivates them to look at the solutions. I think, and also the other part, what is important is that the way you actually dealt with quantum mechanics and some of these fundamental doubts which always is there in the mind of the students, and how those things can be addressed. And that's an advanced physics course. I think why this talk is very important is hardly in India, although we have such courses, but really we do not get into discussing the ways and means of teaching physics or any of the advanced subjects and how to improve the pedagogy of those subjects. I think this is something I had the intention that institute should get into it, and the faculty should get engaged into those activities. In fact, I think this is the first lecture that we are doing in this space, and there we would like to have many more lectures, and we would like to have you maybe in a more active role to get the faculty inspired to develop these techniques, adopting these techniques while teaching physics. Because as you know, you have been in IIT yourself, that IIT classroom has students where there is a diversity. And because of various reasons, we have to handle the diversity in a very sensitive way. And even the ecosystem currently with the students, the degree of anxiety of the students in terms of the career in the Indian context is actually on the rise. And the campus has to be much more sensitive to the anxiety and the tension that the students have. So therefore, that also has to be, that whole spirit and approach has to be embedded in the classroom contact as well. It cannot be only outside the classroom with some special effort. So therefore, the whole approach that you presented, and that's what we actually wanted, that more faculty to get engaged in and to understand. And I think your lecture has really shown the way. And thanks again. It's my personal thank as a friend, and also as a director of the institute, formally also, it's thank you, Chandra.
Well, thank you so much. I really, appreciate having, you inviting me, because it's always fun. And I do agree with you a lot. Several things that you mentioned. I mean, one thing is like, learning, collaborative learning. Another aspect that I didn't get that much opportunity to emphasize is that doing these kinds of things in class in this low anxiety, low stakes environment is also developing a skill in students that is really important in life. I would say that one major difference that I see, like between India and US, like even at the K through 12 level, that means like, until high school, is that there is a lot more collaborative learning happening in the United States here. And so students actually are much more, much better at communicating and presenting themselves. And I think that that is a skill that a lot of times, in Indian schools, we don't actually develop. But if you look at the employers, if you look at ABET is basically the accreditation agency here for engineering. What you see is that, the kinds of things that they have actually found to be the most useful for students is ability to communicate, ability to actually solve problems in general, ability to actually lead a team, ability to be led, because ability to be led is important too. By led, I mean like, you can be part of a team and still make important contribution where you are not the leader. Ability. So these are skills that you learn if you actually work with other students in class in these low stakes environment. Also, the other thing that you said, Shantanu, that actually reminded me that we have done a lot of work also on like, how will you assess student learning? Should you actually have a lot of low stakes things in addition to any exams and things that you're giving? And I would say yes, if you can actually grade students on a lot of low stakes things, not just on like 2 exams, one midterm and one final exam, that would be much better, because a lot of times students even have a higher level of anxiety if 50% of their grade depends upon midterm and 50% on final exam, because it's like 2 times if you didn't do well, you are just basically sunk. So if you actually grade them on homework or quizzes throughout the semester, first of all, it will also space their practice, because if students know that each week there is going to be a quiz in the collaborative problem solving class, they are actually going to review those things and learn. And that way your learning will be spaced, because when you actually space your practice, you learn much better than when your practice is all crammed at one point. So right before the midterm, you're just opening the book, or right before the final exam. So not only does it space the practice, in which case people organize and extend their knowledge in ways that are much more robust, and the rate of forgetting is much slower, they will actually also learn in a way where they won't be too anxious about just having 2 exams determine everything in the course. So I think that that is one thing for reducing anxiety. Also, making the grade of one student not depend upon other student is also an important thing. So I don't, I cannot emphasize the importance of like not doing grading based upon, I'm only going to give 20% A's, and these 20% students are going to be like the top students in this class, and the rest is going to get everything. In the US, there is more and more movement towards removing anything of that sort, and all students should be like, graded based upon, how they are doing, and not like their relative performance relative to other students. So I think that in that sense, being more generous can only, can make students be more interested in learning, and also collaborative learning will increase outside of class also, because if students think that, oh, my grade is going to depend upon your grade, they may not want to collaborate with each other. And notice that, like, we want students to be able to collaborate with each other outside and inside of class. So again, thank you so much for having me, and special thanks to Shantanu, and for having me here.
Thank you, Professor Chandralekha. There was actually a huge crowd around, including online and offline. There were about 120 participants. It's a huge crowd for our scale. It's a new initiative from the Department of Physics. Thank you for joining, and we look forward to interacting with you again in future.
Thank you so much. Thanks a lot for having me. Thank you so much.
Bye.
Thank you. Bye-bye.
Bye, Chandra.